Okay, this is continuing on with the cranial nerves, and this is going to be protection of the CNS, and we're going to jump into the one following it, which is going to be the spinal cord, so it's all going to run together. So starting out for the CNS, or the protection of the CNS, we have the skin, which is our first or outermost layer. Following that, we have periosteum, which is the covering of the bone, which is our next layer, followed by the first layer of the meninges, which is the Dura Mater. Following that, we have the arachnoid, and these are all connected. These actually all touch. Between the arachnoid, so this is our first and second of the meninges, and then our third layer is the Pia Mater, but between the arachnoid and the Pia Mater, there's the subarachnoid space. And in the subarachnoid space, that's where we find the CSF. So we have skin, which is the outermost layer, followed by periosteum, followed by bone, followed by the Dura Mater, the arachnoid space. Then that's just the arachnoid, followed by the arachnoid space, which is where you find CSF, central cerebral, spinal fluid, and then finally the Pia Mater. And another way to remember this is the meninges pad the brain. And this is kind of going in reverse. This is like your innermost layer to the skull, followed by the arachnoid space, which is the next layer out, and then the Dura Mater, so this is the third layer out. So then your brain would be this layer, and then it's going that direction out. So pad, if you can remember that. This is kind of a layered view, but to give you a better idea of how it's structured, let's say we have, we can do, okay, so this layer right here is going to be the Pia Mater. And I left these little breaks in here because this is how arteries pass from outside in the cerebral spinal fluid into the brain. So then in here this is not 100% anatomically correct, but we have our actual, this is where the brain is. And then after the Pia Mater, we have the arachnoid space, and I'll just put AS. And then the first layer after the arachnoid space is the arachnoid. And then the layer on top of that, which is a little bit thicker, is the Dura Mater. So in this area we have cerebral spinal fluid kind of floating around, And this is why when we hit our head, we don't always get a concussion. The cerebral spinal fluid kind of cushions the brain. Also throughout there, it's not just fluid. You're going to have neurons and arteries and blood supply. So there's a lot going on in the subarachnoid space. And again, these layers up are all connected, but the Pia Mater is actually what's connecting to the brain. So your brain is kind of free floating there. So what happens is if you hit your head, and if you've ever heard of a subarachnoid bleed, all that is a hemorrhaging, because you have blood supply going all the way throughout here, coming and going. If you were to get or hit your head and you start to get a bleed, this is what would be considered a subarachnoid bleed, because it's happening in disregard that. This is the subarachnoid. It's SA. Sorry about that. And then if you had a subdural bleed, that's going to be between the dura and the arachnoid. So this would be a subdural bleed happening up here. So moving on, sorry, that was a little bit of a mess of an illustration. With the spine, it also has the meninges, but the spine's kind of set up a little bit differently. So I'll go into it briefly. So if this is your spine, and this is the spinal column right in here, or we'll just put SC for spinal cord, you have, again, the Pia Mater is the lining closest to the core, so it's just a real thin line. And then you have, again, another space, which is kind of like the subarachnoid space. It's an equivalence. And then you have the arachnoid and the dura mater. The difference with the spinal cord, and these are a little out of proportion, I apologize, between the spinal cord and the, I guess, the very outside, you have a layer of, there's some fatty tissue. So if this was kind of coming out, so when you inject, the dura mater is actually not connected to the very outside. There's a little space of fatty tissue around the spine that you can inject local anesthetics into, and then that kind of seeps through and then gets to the nerves, and then will cause local numbness to whatever you're trying to work on. Real fast, we'll move on to concussions. And for concussions, all it is an injury to the brain that's temporary. of people like to say that it is a bruise, but it's not necessarily. It's just temporary dysfunction or of the brain from impact. And what happens is, we kind of talked about the CSF fluid. You have your brain, and then you have your skull, and then we have CSF fluid. But what happens is, if you take impact hard enough, your brain will hit against the skull, and you'll get temporary damage. And the symptoms you see is partially determined by where your brain hits, but also remember, just kind of like whiplash in a car, if you hit the front of your head and your brain goes this way, it will also rebound this way and can smack the back of the skull. So that's a concussion. The difference, that's really kind of minor when you think about it, but it's how they break down the difference, is a concussion is microscopic. Injuries, and it is widespread. So it'll kind of take or be a huge kind of impact area that it affects. With a brain contusion, it is macroscopic. And it's localized. And it is actual bruising of the brain. And if you were to take this brain up here and we were to just cut it in half and then rotate it, and we were looking at the brain, if someone got hit hard enough, what you would see is actual bruising of the area. And it'll be over the surface, and it'll kind of get a little bit narrower, generally into the brain. So if someone hit, with a hammer or any other object that's more blunt, instead of just falling, it'll actually cause bruising. And the problem with bruising, as we know, with wounds and everything else, it brings blood to the area, and if you get too much blood in there, you can get swelling going on in the brain, and that can cause a bunch of issues. It can also hemorrhage and start to leak out into the arachnoid space and other areas, and cause a brain bleed. So that's another, I can't spell today, another issue that you have to be careful of. As far as strokes, he put down CVA/stroke. There's several types, but he just wants us to know in general. So you can have a clot that originates from somewhere else. So you could have a clot from the heart, from bad cholesterol or anything going on, and it will flow through the arteries, and it'll actually get stuck, and then your red blood cells will start to pile up behind it, and they'll be able to this way, and then this tissue after this point won't be able to get any oxygenation or nutrients, and slowly all the cells will just start to die, and you'll kind of get this mass of dead cells. With ischemic, what it is actually where the wall starts to occlude. And again, you'll see red blood cells starting to kind of pile up behind it. And they can normally go in and fix this, but eventually it'll occlude all the way, and you'll get the same result. It'll kill off all the tissue and cells past that point, With a mini stroke, the difference is TIAs. They last less than 24 hours. And sometimes it's a complete blockage, and other times it's a partial blockage, so blood flow can still kind of get through, but because of the decrease, you'll start to see symptoms happening. But eventually, like this clot up here, will eventually break free and everything will be restored, and that's why they say that these mini strokes eventually add up to a larger stroke, because there's an underlying problem to why that clot formed in the beginning. Moving on to the diseases, there's Alzheimer's. And it affects 1 in 10 over the age of 65. And it starts in the hippocampus. And then it moves outwards. And we know that everything is kind of processed through the thalamus and the hippocampus. This is where it originates, and then what it is it's abnormal cells. I'll kind of just draw them like this, and they attack normal cells inside of the hippocampus. So that's where you'll start to see kind of the deterioration start, and it'll move out of the hippocampus and it'll move to the area of speech, and then you'll see speech start to decline. So then speech will go out, and then it'll move on, and it'll affect someone's logic, and then it'll move on and affect emotion. And it'll kind of come full circle to sensory. And then at the very end, it'll start to affect old memories. And so these cells will start to destroy the hippocampus. And then after they've destroyed the hippocampus, they move on to different parts of the brain. So they kind of just cycle through the brain, and then the symptoms that you see for Alzheimer's is showing you what part of the brain is being destroyed. And it normally takes 8 to 10 years for it to run its full cycle, or for it to actually be fatal. And eventually it'll start to destroy the autonomic process of the brain, so it'll destroy what we need for respirations and heart rate, and that's generally when it becomes fatal, or what is the cause of death for most Alzheimer's patients. Next we have Parkinson's. And inside the basal ganglia, there is the substantia nigra. Sorry if I'm butchering that. And this is located in the midbrain. And what it's in charge of is the production of dopamine, which is a neurotransmitter. So you have all of these kind of fibers from your neurons, and when they get to the end for the synapses to pass on the message, they need the dopamine to be able to send the signal onward, and there's not enough of it to send the signal, and this is synapsis. And because they can't send the signal, that's when or why you get jerking movements. Everything's kind of slowed, and that's pretty much you'll get the twitching, and it's all this is in charge of motor function. So that's why you start to see the kind of twitching aspect of it. Moving on to, let's see. Huntington's disease. Okay, so how to find it. So Huntington's. It affects one out of every 10,000 people. And there's a 50% chance of passing it on. And again, this takes part in the basal cell ganglia, or the basal ganglia. And it's in charge of movement, and organized thoughts. And so first you'll see they'll start to get kind of clumsy, and they'll have abnormal movements. They'll start to become spacey, kind of forget everyday things. Eventually emotion is involved, and it starts to deteriorate, and eventually it ends, which is a typical or kind of the telltale sign of Huntington's disease. It's chorea, which in Greek sadly means to dance. And what this is the jerking motion that you see either in movies or with actual Huntington's patients. It's uncontrollable twitching and movements of the body, and that is all from deterioration of the basal cell ganglia. And it's mostly seen in people ages 30 to 50 generally. There is adolescent Huntington's, but generally age 30 to 50, and it takes 10 to 20 years to run its course. Anyway, I hope that helps you guys out. Let me know if you have any questions.